So in this lecture, we want to talk about electric fields. Now, there's a lot to know about electric fields in theory, but for the MCAT, I think we really just need a very bare bones understanding of it. So I'll try and give you that here. And so to start with, let's say we've got a charge Q positive, and I'm not going to tell you what its specific charge is. Let's say it's a certain number of coulombs positive. Then we've got a Q negative, right? And of course, that means that there's going to be an attraction between them. And the way that we would draw that attraction, so I've been drawing it like this, right? I've been saying that they're kind of attracted to each other. They're both pulled toward each other. But there's a particular convention that we like to do for physics. And this convention, you do need to know this convention for the MCAT. And it's that positive charges will generally attract negative charges. And we'll draw the arrows coming away from the positive charges and toward the negative charges. So this is what we would call an electric field. Again, the convention of which way we draw the arrows, it's just a convention. We could draw it the other way, but the way that the field as a whole, no pun intended, the way the field as a whole draws the arrows is always from the positive charge to the negative charge. And in general, we'll draw more than one arrow. So I just drew one arrow here, but let me show you what it would look like. So I borrowed these images from Wikipedia, and this kind of shows the electric field coming off a positive charge and the electric field of a negative charge. And again, we see the arrows coming toward the negative and away from the positive. And again, that's just a convention. Now, if the charges were to interact, it would look something like this. And so I want to draw your attention to a couple of things. First of all, again, the arrows are always coming off the positive charges. And second of all, the density of the arrows, how close together the arrows are, tells us how strong the charge is, or tells us how strong the electric field is. So for example, we see here that the arrows are very far apart, they're not very dense, and so the electric field is very weak in this area. But here, they're very, very close together, and so that means that the electric field is much stronger. And so naturally, as we get closer to the charge, the electric field is going to get stronger, and as we get further away from the charge, the electric field is going to get weaker. Right? And that has to do with the inverse square law that we talked about in the last lecture on Coulomb's law. And so as long as we know how to read these diagrams on a basic level, then we can read even really weird diagrams. So let me show you this, for example. So I borrowed this diagram off Wikipedia, and I really have no clue what's going on here. Right? There's a bunch of weird shapes, bunch of weird stuff, and I don't really know, and it doesn't really matter because I know how to read these diagrams, right? I know that there's a lot of density here, and that means that the electric field, the force of the electric field is going to be very strong in this area, for example. It's going to be very strong in this area, and it's going to be very weak here, right? There aren't that many arrows. And furthermore, I also know what would happen if I were to put a positive charge somewhere. So these arrows represent the direction of movement if I were to drop a positive charge somewhere. So for example, if I were to drop a positive charge here, or actually if I were to drop one here, then what's going to happen is it's going to get repelled by this positive charge. It might get dragged a little bit toward this, but then it's ultimately going to go this way. And so again, the arrows, which we drew up here, represent if I were to drop a random positive charge somewhere, it's going to go toward the negative charge and away from the positive charge. And in this case, if I were to drop a positive charge here, right, over here, then it's going to go away from the positive and then ultimately toward the negative, right? But maybe if I were to drop it here, it's going to go so far up that it's not actually going to go back down. And so, again, from reading these, we know many things. We know the strength of the electric field in a given location, and we know what's going to happen to a positive charge. And by the way, we also know what's going to happen to a negative charge because it's going to just move in the opposite direction. So, for example, if I were to drop a negative charge over here, then it's going to, rather than move this way, it's going to move this way, right? It's going to get attracted to this positive. And so again, even with really weird electric field diagrams that we don't really know what's going on, that are kind of weird, we can read them and we can have a basic understanding of what's going to happen just by understanding how to read these diagrams with a couple basic principles. Now, actually calculating the strength of these electric fields is well beyond the scope of the MCAT. It typically requires some type of calculus. And so doing this quantitatively is not on the table for the MCAT, at least as far as point charges go. Now, there is one scenario where we will need to know how to do this for the MCAT, and that's what we call a uniform electric field. And so let's say instead of a point charge like this, let's say we've got two plates. We've got plate 1, and we've got plate 2. And this plate is positively charged, and this plate is going to be negatively charged. And what we mean by uniform in the context of these plates is that the charge is going to be evenly distributed all across these plates. So it's not going to be concentrated in one location or another. It's going to be evenly distributed, right? And that's true both for the positive and for the negative. And so if we were to draw the electric field lines, what would they look like? Well, remember, we want to draw them from the positive to the negative. So they're going to do this. That is to say, they're going to be the same distance apart in every location, right? So the density of these lines doesn't increase or decrease. They're always the same distance apart. And that means that we've got what we call a uniform electric field. This is what we mean by uniform. It means that the electric field is even all throughout. Now, at the edges, it might do some weird stuff like this, but we typically don't consider the edges when we're dealing with this, at least not on the MCAT. Right, so we can kind of ignore the edges, and we can look at this, and we can kind of pretend that it's an endless electric field going all the way up and all the way down. And really, this would be three-dimensional. So if you were looking at this on a three-dimensional level, it would kind of look like this. Right, they would be three-dimensional plates. But again, the important thing is that the electric field is uniform. Now, what would happen if I were to drop a charge somewhere along this electric field? Let's say I were to drop a charge here, right? Well, what's going to happen is the charge is going to experience some kind of a force, right? And it actually doesn't matter where we drop it. It doesn't matter if we drop it, for example, here, here, or here. It's always going to experience the same force. So this is also what we mean by a uniform electric field, right? Why is that? And that's because if the charge is over here, for example, then the force it experiences due to this is going to be very high, but the force it experiences due to this is going to be very low because it's so far away from this plate. If it's in the middle, then the forces are going to be kind of moderate from both sides. And so it turns out that no matter which side, or no matter where a charge is along this uniform electric field, it's the force it experiences is always going to be the same. And again, we can understand that mathematically using using Coulomb's law, F equals Q over R squared, where we would have to calculate that for each of these plates, right? For a given charge, we'd have to calculate that for each of these plates, and it would turn out it would be even no matter where the charge was. But we could also, by the way, calculate this or understand this more intuitively, perhaps from a conceptual standpoint, just by looking at the arrows, right? So the arrows are always the same distance apart, and that means that the field is uniform. And so what is that force? So quantitatively, this is where we do need to understand some quantitative background. F is equal to Q, and that's the charge of the particular charge that we drop. So actually, since we're using orange, let me go ahead and switch some of these colors. And so again, Q is going to be the charge of the thing that we drop, whatever it is. Q times E. And E is going to be the strength of the electric field. And let's go ahead and talk about units for this. So of course, force is in newtons. Q, of course, is in coulombs. And so naturally, E is going to be in newtons per coulomb. So fairly straightforward. Again, E is the strength of the electric field. So if we wanted to, for example, we could rewrite this equation, and you'll often see this in textbooks, as E is equal to the force that a given charge would experience divided by that charge. And so another equation that we can use is that electric field strength is also equal to the voltage. And remember, voltage is electric potential, right? The potential difference between this and between the positive and negative plates, right? Or essentially, how badly do the charges want to jump from here to here, right? And that's the voltage divided by the distance between the plates. And so both of these equations are going to be useful for understanding this for the MCAT. And so zooming out, if we were to look at this, what this would mean is that if I were to give you the charge of a given charge, right? Let's say we were to drop a charge and I were to tell you it is like 5 coulombs, right? You'd be able to calculate the force that charge is experiencing. And you would also, by the way, know the direction that the charge is going to move, right? If it's a positive charge, it's going to move this way. If it's a negative charge, it's going to move this way, right? And you could do that if you were given So for example, if you were given the strength of the electric field, or maybe not the strength of the electric field, but maybe you were given the voltage difference and the distance between the objects, then you could use that to calculate the strength of the electric field, and you could plug that into this equation, and you could figure out the force that the charge is going to experience, that the object is going to experience, right? And from that, you could, of course, plug that into F equals ma and figure out how much the charge is going to accelerate. So just notice how all these equations are really related, and when we know them, we can plug them into one another, and really that'll help us to understand, how things are going to move and what's going to happen. And so we'll have some practice problems where I'll ask you to use some of these equations. But if we were to zoom out, these equations are what we want to know for electric fields for the MCAT. Again, we want to focus on uniform electric fields and understanding this equation, or looking at it in the form over here, right? E is equal to force divided by Q, which is also equal to the voltage divided by the distance between the plates. And so that's all we need to know for electric fields for the MCAT.